Notre-Dame Cathedral in Paris is completely engulfed by fire.
Many things are said to be irreplaceable. Great art, cultural heritage, symbols of protection and hope. What word should we use when it's all of these?
Welcome to Grandeur Decoded, where we reveal the hidden engineering, strategy, and human ingenuity behind the world's most iconic creations. And today, we're decoding one of the greatest engineering comebacks ever attempted, the rebirth of Notre-Dame Cathedral. When the roof ignited on April 15, 2019, the world didn't just watch a church burn, it watched centuries of engineering, craftsmanship, and cultural identity teeter on the edge of collapse. What came next wasn't just a restoration, it was a fusion of medieval knowledge, 19th century ambition, and 21st century technology, unlike anything attempted on a historical monument before. These are the 10 decoded facts behind the Reborn Notre-Dame. The first thing to understand is how dangerously close the cathedral came to structural failure. The fire began in the attic, a dense network of oak beams, some dating back to the 12th century. Builders in the 11th century had used enormous logs, entire trees, to create trusses that stabilized the stone vaults below. Once the fire reached them, those beams burned like a dry forest hit by a blowtorch. As temperatures soared, the limestone vaults acted like the only barrier preventing the inferno from dropping straight into the interior. But limestone behaves strangely under extreme heat. When it approaches 700 to 800 degrees Celsius, it begins to lose chemically bound water, making it brittle and prone to cracking. Engineers later said that if even one major vault had opened, it could have triggered a redistribution of forces severe enough to compromise the tower's firefighters, knowing the bells could rip the towers apart if they fell, fought for hours to keep water from hitting the wrong structural elements. In the end, the cathedral survived because stone absorbed just enough energy and firefighters made just enough correct decisions at exactly the right moments. The second decoded fact is the role of a digital map that shouldn't have existed. Years before the fire, art historian Andrew Tallon spent years laser scanning every inch of Notre Dame. His work captured the cathedral's real geometry, lean, asymmetrical, slightly crooked in places, exactly as centuries of settling had shaped it. Laser scanning at that time wasn't standard practice for medieval structures, and Tallon's scans weren't made for reconstruction. They were created to answer historical questions about how Gothic builders achieved their feats. After the fire, that data became priceless. Engineers could compare damaged stones with Tallon's baseline, identify where vaults sagged by millimeters, and understand which cracks were new and which were centuries old. Medieval architects didn't leave blueprints. Tallon had created the closest thing the modern world will ever have to one. The third fact takes us into the most ambitious and controversial decision of the entire rebuild: recreating the timber framework using medieval carpentry. The original forest wasn't just massive, it was structurally intelligent. Medieval carpenters selected oak because its strength increases as it dries, its density makes it slow to ignite, and its natural flexibility helps distribute loads from the heavy stone roof. Replacing the timber with steel might have seemed like the modern choice, but it would have changed how the cathedral handles temperature swings, vibration from the bells, and even wind shear. So France committed to reconstructing the attic as it was originally built. More than 1,000 oak trees, sourced from carefully managed French forests, were cut, dried, shaped with hand tools, and fitted with traditional joints. Carpenters had to revive medieval techniques long out of practice, but they also used 3D models to predict how each truss would move with humidity, weight, and thermal expansion. It is one of the rare moments where medieval and modern engineering worked with the same goal, not copying the past, but preserving the logic that made the past work. The fourth decoded fact examines the spire. Viollet-le-Duc's 19th century spire was a reinterpretation of what had once stood on the cathedral, blending Gothic revival style with structural clarity. When it burned and fell, France faced a choice: redesign it for the modern age, or rebuild it in the spirit of the original. Restoring it required sourcing and shaping nearly 80 tons of oak for the spire's frame, covered with lead sheets that match its historical weight and behavior under weather. But this time, engineers added modern lightning protection, improved anchorage systems designed to distribute force more evenly into the transept, and subtle internal reinforcements that won't be visible to the public. The new spire isn't a replica. It's a structurally improved continuation of Viollet-le-Duc's vision, strengthened by the kind of data he never had. The fifth fact reveals why the period after the fire was even more dangerous than the fire itself. Before reconstruction could start, workers faced the mangled remains of scaffolding that had been installed for roof cleaning before the blaze. The heat had warped the metal into something closer to a collapsed bridge than a maintenance structure. Removing it required teams to suspend themselves inside the remains of the roof cavity, cutting and removing pipes one by one without disturbing the fragile stone around them. Engineers also had to install temporary wooden arches under weakened vaults, massive curved supports that mirrored the original Gothic geometry. These supports acted like giant orthopedic braces, holding the cathedral steady while crews assessed damage. Stabilizing Notre Dame became a separate engineering project of its own, requiring constant monitoring, sensors placed in critical joints, and detailed mapping of every fracture. The sixth decoded fact focuses on the stained glass windows, including iconic 13th century pieces. While the flames never reached them, heat and airborne lead dust posed serious threats. Lead from the roof melted and vaporized, coating surfaces throughout the building with a fine particulate that can chemically interact with medieval pigments. Cleaning the glass became one of the most delicate operations in the entire restoration. Conservators used microvacuums and chemical stabilizers, carefully removing deposits without stripping centuries-old paint. In some cases, they used laser cleaning, pulses of light that remove contaminants without touching the glass beneath. Each window also underwent structural reinforcement to ensure the columns, the lead strips holding each piece together, could carry their load for centuries to come. Their survival wasn't accidental. It was the result of some of the most meticulous conservation work France has ever undertaken. The seventh decoded fact explains how France rebuilt a structure this large in only 5 years. Instead of working sequentially, carpenters after roofers after stonecutters, France created a nationwide assembly line. Timber framing workshops shaped trusses, while stone experts repaired vaulting glass was restored in specialized studios, while metalworkers recast roofing panels. Rope access specialists mapped hard-to-reach damage, while acoustic engineers assessed how structural shifts might affect sound inside the cathedral. Over 200 companies collaborated simultaneously, a logistical feat closer to managing a space mission than restoring a building. The pace was unprecedented, not because tasks were rushed, but because so many were performed in parallel. The eighth fact reveals how Notre Dame is now far better protected from fire than at any point in its long history. The rebuilt attic includes a network of thermal sensors, smoke detectors, and a water mist system designed to suppress flames without overwhelming the stone vaults. With water, firefighters now have access routes built directly into the attic, allowing them to reach hotspots quickly, something that was nearly impossible in 2019. Engineers studied airflow patterns, potential ignition points, and structural vulnerabilities, then integrated discrete solutions to prevent a similar disaster. The result is a fire protection system that remains invisible to visitors, but fundamentally changes the building's resilience. The ninth decoded fact highlights a debate that divided architects and citizens, whether Notre Dame should return as it was or embrace a modern design. Some proposals included contemporary materials, glass roofs, and spires that signaled France's future rather than its past. But modern materials behave differently under wind and thermal load. A lightweight contemporary roof, for example, could have altered how forces travel through the cathedral's stone. Ultimately, historical continuity wasn't just a cultural choice, it was a structural one. Preserving the cathedral's identity also preserved the engineering logic that had kept it standing for centuries. And the 10th decoded fact brings us to the essence of the restoration. Notre Dame today is the first time medieval 19th century and 21st century engineering have coexisted inside the same structure. The stone skeleton reflects the genius of its original builders. The spire echoes Viollet-le-Duc's Gothic imagination. And the new roof combines traditional craftsmanship with digital modeling, environmental monitoring, and advanced fire protection. The cathedral that stands now is not a replica of the past. It's a deeply informed continuation of it, built with knowledge from 3 eras and designed to survive for many more. Notre Dame was nearly lost in a single night. It was rebuilt through thousands of hands, millions of hours, and the combined intelligence of centuries. What stands today isn't just a restored monument. It's one of the greatest demonstrations of human ingenuity ever completed, and a reminder that when history is threatened, engineering can bring it back to life.